Hi everybody, welcome to AS Engineering College YouTube channel and the course Discrete Mathematics. The topics for today's session are partial ordering relations, which is nothing but partial orders, total ordering relations, that is total orders, assay diagram, functions, types of functions, composition of functions, and we discussed some previous gate questions. So partial orders, before I explain about the partial order, let me quickly recollect the things which I have explained in the previous session. In the previous session I explained about the equivalence relation. Equivalence relation means any binary relation which satisfies reflexive property, symmetric property and transitive property, then it is equivalence relation. So reflexive property means for every element in set A there is a mapping to itself, then it is called reflexive relation. Symmetric relation means if there is a relation from A to B and B to A, then that property is called symmetric property. And then transitive property. Transitive property means if there is a relation from A to B and B to C, then there must be the relation from A to C. If any binary relation satisfies these three properties, then it is called equivalence relation. Now we'll see what is the partial ordering relation. So partial ordering relation, here I am taking relation A on the set. I am taking the relation R on the set A is said to be partial ordering relation or partial order on the set A if it satisfies reflexive property on A, next antisymmetric property on A, and then transitive property on A. So if the binary relation A satisfies these three properties, which is nothing but reflexive property. So reflexive property is nothing but for every element, for all A belongs to capital A comma A belongs to R, which is nothing but every element is mapped to itself under the relation R, then it is called reflexive relation. And then antisymmetric relation. Antisymmetric relation means if there is A comma B belongs to R, comma B comma A belongs to R, then A must be equal to B. This is called antisymmetric property. The antisymmetric property says that if there is a relation from A to B and B to A and B must be equal to each other, then it is called antisymmetric property. And the next one is transitive property. Transitive property says if there is a mapping from A to B, comma B to C, then there must be the relation from A to C. This is called transitive property. So if there is a order pair A comma B and B comma C, then there must be the order pair A comma C in R. Then we say that that relation is transitive relation. If the relation satisfies these three properties, then it is called partial ordering relation. Now what is the equivalence relation? Equivalence relation means reflexive, symmetric and transitive. Partial ordering relation means reflexive, antisymmetric and transitive. The main difference between equivalence relation and partial ordering relation is that the second property. If the relation satisfies symmetric property, reflexive and transitive, then that is equivalence relation. If the relation satisfies reflexive, antisymmetric and transitive, then it is called partial ordering relation. Next, a set capital A with a partial order or defined on it is called partially ordered set or ordered set or poset. So this is and is denoted by like this. Here, this is called order. This is the order pair, which is nothing but post set. In this, R is the partial ordering relation defined on the set A. If a partial ordering relation R defined on the set A, then A comma R is called post set. Post set is nothing but partial ordering set. Now we'll see the examples for this partial ordering relation. Now here I am taking the relation. First I am taking the less than or equal to. I am taking the relation is less than or equal to. This is the relation which is defined on set of all real numbers. R is nothing but set of all real numbers. So I am taking some relation. That relation is less than or equal to, and I am taking the set of all real numbers. Now I am going to verify whether is less than or equal to one set of all real numbers is partial ordering relation or not. First, I am going to verify whether it is satisfying reflexive property or not. Here the relation is either less or equal. If you take some A belongs to R, if you take some real number, then A is equal to A. Then A is equal to A. So if you take any real number A, then it must be equal to itself. It will be equal to itself. Here the relation is either less or equal. This is the relation which I am taking, less than or equal to. So for any element A belongs to R, we have A is equal to A. That is A comma A belongs to R. That is A comma A belongs to R. That means the relation R is reflexive. The relation R is reflexive. What is the R relation here? Less than or equal to. The relation less than or equal to is reflexive. Next I am going to verify whether it is antisymmetric or not. Whether it is antisymmetric or not. So to verify this, I am taking two elements. A comma B belongs to set of all real numbers. I am taking two elements. A comma B belongs to set of all real numbers. Now here, if A is less than or equal to B and B is less than or equal to A. If A is less than or equal to B and B is less than or equal to A, then A and B must be equal. And A, B and B must be equal. So here, if there is A comma B and B comma A, then if it is satisfying equal, A is equal to B, then it is antisymmetric. Otherwise, it is not antisymmetric. So I am taking two elements in the real number system, small a and small b. If A is less than or equal to B and B is less than or equal to A, then A and B must be equal. Therefore, the relation R is antisymmetric. The relation R is antisymmetric means the relation less than or equal to. The relation less than or equal to is antisymmetric. So next I am verifying the transitive relation. So I am taking three elements. A comma B comma C belongs to set of all real numbers. If A is less than or equal to B and B is less than or equal to C, then A must be less than or equal to C. Take any three real numbers, A comma B comma C. If A is less than or equal to B, B is less than or equal to C, then A must be less than or equal to C, which is nothing but A comma B belongs to R and B comma C belongs to R, then A comma C belongs to R. Then A comma C belongs to R. That is, the relation less than or equal to is transitive. The relation less than or equal to is transitive. That means the relation less than or equal to is satisfying reflexive property, antisymmetric property and transitive property. Therefore, the relation less than or equal to is partial ordering relation, and r comma less than or equal to is a poset. R comma less than or equal to is a poset. So here R is the partial ordering relation defined on a set of all real numbers. Therefore, the relation is less than or equal to is partial ordering relation. Similarly, we will see greater than or equal to. The relation is greater than or equal to. Greater than or equal to on set of all real numbers. I am taking the relation greater than or equal to on set of all real numbers. R is real numbers, set of all real numbers. First, reflexive property. If you take any element A belongs to R, then A is equal to A. Here the relation is either greater or equal. The relation is either greater or equal. So here for any element in real number system, A is equal to A. That is A comma A belongs to R. A comma A belongs to R. Here R is the relation greater than or equal to. That is R is reflexive. R is nothing but greater than or equal to. The relation greater than or equal to is reflexive. Next, antisymmetric property. So I am taking two elements A comma B belongs to set of all real numbers. If A is greater than or equal to B and B is greater than or equal to A, then A is equal to B. Then A is equal to B. So if A is greater than or equal to B, B is greater than or equal to A, then that is possible only when A and B are equal. Therefore, the relation greater than or equal to is antisymmetric. The relation greater than or equal to is antisymmetric relation. Now next one is transitive relation. A comma B comma C belongs to R. So if A is less than or equal to B and B is less than or equal to C, then A is less than or equal to, it's greater than or equal to if A is greater than or equal to B, B is greater than or equal to C, then A must be greater than or equal to C. Take any three real numbers A comma B comma C. If A is greater than or equal to B and B is greater than or equal to C, then A must be greater than or equal to C. If you want to take some example, take 2 comma 3 comma 4. 2 comma 3 comma 4. 4 is greater than or equal to 3. 3 is greater than or equal to 2. Obviously 4 is greater than or equal to 2. Here A is 2, B is 3, like that. So if 4 is greater than or equal to 3, 3 is greater than or equal to 2, then 4 will be greater than or equal to 2. This is called transitive property. So the relation greater than or equal to is satisfying reflexive property, antisymmetric property and transitive property. Therefore, greater than or equal to is a partial ordering relation, and greater than or equal to comma or comma greater than or equal to is a poset. This is poset. So here R is greater than or equal to is the partial ordering relation defined on the set of all real numbers. So the relation is less than or equal to and is greater than or equal to are partial ordering relation on set of all real numbers. We'll see one more example. The example is this. I am taking the relation subset. I am taking the relation subset. The relation subset defined on P of A. P of A is nothing but the power set of A. So P of A is obtained by taking the set of all subsets of given set A. P of A is partial ordering relation. So here P of A comma subset is a partial ordering relation, that is P of A comma subset is a poset. I'll explain why it is poset. Point number one, first one, reflexive. If you take any set A belongs to P of A, I am taking one set A belongs to P of A. P of A is the set of all subsets. P of A is consisting of the set of all subsets of A. So if A belongs to P of A, then every set is a subset of itself. Take any set that itself is a subset. A is a subset of itself. That is A comma A belongs to R. A comma A belongs to R. So the relation subset is satisfying reflexive relation. Therefore, subset is reflexive. The relation subset satisfies reflexive property. Now the second one, I am taking two sets. A comma B belongs to P of A. If A comma B belongs to P of A, and if A is subset of B and B is subset of A, then A must be equal to B. Then A must be equal to B. That means if two sets are equal, then A will be subset of B and B will be subset of A. Therefore, the relation subset is antisymmetric. The relation subset satisfies antisymmetric property also. Now coming to the third one, transitive property. I am taking three sets. A comma B comma C belongs to P of A. So I am taking three sets from the power set. For these three sets, if A is subset of B and B is subset of C, if A is subset of B and B is subset of C, then A must be subset of C. Then A must be subset of C. So A is subset of B means all the elements which are there in A must be there in B. B is subset of C means all the elements which are there in B or must be there in C. Therefore, obviously, all the elements what are there in C will be there in, all the elements which are there in A will be there in C also. That is, if A is subset of B, B is subset of C, then A will be subset of C. That is, the relation subset satisfies transitive property also. So, the relation subset is satisfying reflexive property, antisymmetric property and transitive property. Therefore, subset is a partial ordering relation defined on the set of all subsets of A, that is P of A. Therefore, P of A comma subset is a poset. Here, subset is a partial ordering relation defined on the set of all subsets of A. So, whatever relation we have taken, that is a partial ordering relation on set of all subsets. I will explain one more example, that is Z plus comma divisibility. So, this is the symbol which we use for the divisibility, and this is Z plus. Z plus, the set of all positive integers. Z of all positive integers. So, I am taking the relation divisibility on set of all positive integers. Now I am going to verify this divisibility is reflexive, antisymmetric and transitive or not. If the divisibility is reflexive, symmetric, antisymmetric and transitive, then obviously it is partial ordering relation. Now we will see first one, that is reflexive relation. I am taking some element A belongs to Z plus. I am taking one element A belongs to Z plus. So we all know that every element is divisible by itself. Every element divides itself. If you take any element, The element may be any element, that is the arbitrary element. It can be 2, 3, 4 or anything. 2 divides 2, 3 divides 3, 4 divides 4. Therefore, every element will be divisible by itself. That is A divides A, which is nothing but A comma A belongs to R. So here A divides A is nothing but A comma A belongs to R. So the relation R is divisibility. The relation R is divisibility. That is, every element is going to divide itself. So therefore R is, that is divisibility is reflexive. Next, the second one is antisymmetric. A comma B belongs to Z plus. A comma B belongs to Z plus. If A divides B, if A divides B and B divides C, B divides A. If A divides B and B divides A, then it is possible only when both of them are equal. If A is dividing B, B is dividing A, then both of them must be equal. Then only it is possible. If one number is dividing another number, another even number is dividing this number, means when they are equal. If both of them are equal, then only it is possible. Therefore, the relation divisibility is antisymmetric. The relation divisibility is antisymmetric. Now I will see the transitive relation. So I am taking three elements. A comma B comma C belongs to Z plus. If A divides B, if A divides B and B divides C and B divides C, then A will divide C. A divides C. If A divides B, B divides C, then A divides C. So if A is dividing B, B is dividing C, then A will definitely divide C. That you can see with this example. 2 divides 4. 4 divides 8. Obviously 2 divides 8. So I am taking A is equal to 2, B is equal to 4, C is equal to 8. 2 is dividing 4. 4 is dividing S. Obviously 2 will divide C. Therefore, the relation divisibility is transitive. The relation divisibility is transitive. Therefore, the relation divisibility satisfies reflexive property, antisymmetric property, and transitive property. Therefore, divisibility is a partial ordering relation, which is nothing but Z plus comma divisibility is a poset. So this is divisibility relation is a partial ordering relation on set of all positive indices. Therefore, Z plus comma divisibility is a poset. This is about the poset. Poset is nothing but a partial ordering relation defined on the set E. So here divisibility is partial ordering relation defined on the set Z plus. Then this ordered pair is called poset. And this divisibility is called partial ordering relation defined on the set of all positive integers Z plus. So when we say that the given relation is partial ordering relation, if it is satisfying reflexive property, transitive antisymmetric property, and transitive property, then we say that the given relation is partial ordering relation. Now next, Hussey diagram. So here, when the relation is partial ordering relation, then you can draw the Hussey diagram for it. So this Hussey diagram is drawn for only partial ordering relation. If R is not partial ordering relation, then there is no concept of Hussey diagram. So this Hussey diagram is only for partial ordering relation. Now I will explain what is the Hussey diagram. So here, the pictorial representation of a partial order, the pictorial representation of a partial order drawn by adopting the following conventions is called Hussey diagram. So there are three conventions. If we draw the digraph, that means if you draw the graph by using these three conventions, then whatever pictorial representation we are getting, that is called Hussey diagram. So now I'll see what are the conventions. The first convention, we all know that partial orders is nothing but reflexive. Partial ordering relation means it will satisfy reflexive property, antisymmetric property and transitive property. So since the partial order is reflexive, reflexive means there is a mapping from A to A itself. There is a mapping from A to A itself. So at every vertex of a digraph of a partial order contains a loop. So loop is nothing but if the starting and ending vertices are same, then it is called loop. So here the partial ordering relation is reflexive, which means there is a mapping from A to A itself. There is a mapping from A to A itself. That is, the starting and ending vertices are same. Therefore, the partial ordering, therefore, the digraph will be having loops at every vertex. Loops will be at every vertex. So these loops will not be exhibited explicitly. You need not to exhibit all these loops explicitly. For example, if there is a order pair like this, 1, 1, 2, 2, 3, 3, like this, then this ordered pairs will be represented with only dot 1. Dot 1 means you must understand that there is a loop at 1. So the first convention says that since partial ordering relation is reflexive, reflexive is nothing but at every vertex there is a loop, you are not going to exhibit those loops explicitly. That is the convention number 1. So the convention number 2. So this since the partial ordering relation is transitive. So the partial ordering relation satisfies transitive property also. That means there is a edge from U to V and there is a edge from V to W and there will be the edge from U to W. So the transitive property says that if there is a edge from U to V and V to W, there must be the edge from U to W. You need not to exhibit this edge. You need not to exhibit this edge separately. It's understood. That means if there is a edge from U to V and V to W, there must be the edge from U to W. You need not to exhibit that. You need not to exhibit it. That is the second convention. Now the third convention says that to simplify the format of the digraph of the partial order, you are going to represent every vertex with dot. You are going to represent every vertex with dot. And one more thing, if there is a edge like this, if there is a edge A comma B, then A must be downwards and B must be upwards. A must be downwards and B must be upwards. So when there is a edge from A to B, you have to place A downwards and B upwards, so that we understand that there is a relation from A to B. There is a relation from A to B. It doesn't mean that there is a relation from B to A. There will be only relation from A to B. If it is like this, if it is like this, this is 1, this is 2, it means there is a relation from 1 to 2. There is a relation from 1 to 2. Next, like this, 2 to 3, there is a relation from 2 to 3. So since here, to simplify the format of the digraph, you are going to represent every vertex with dot, and if there is a edge from A to B, A must be downwards and B must be pointing upwards. Any digraph which is drawn by using these three conventions, then it is called Hussey diagram. Hussey diagram is the simplification of digraph by using these three conventions. Convention number 1, at every vertex there will be the loop. You need not to exhibit those loops. Next, convention number 2, if there is a edge from U to V and V to W, there must be the edge from U to W. You need not to exhibit the edge U to W separately. And convention number 3, every vertex will be represented with dot, and if there is a edge from A to B, A must be downwards and B must be upwards. Then whatever pictorial representation we are getting, that is called Hussey diagram. Now we'll see one example. then you will be understanding this very clearly. So here I am taking some relation. So what type of relation it is? It must be partial ordering relation. If R is the partial ordering relation, then only you will be able to draw the Hasse diagram. So whatever relation I have taken, that is the partial ordering relation defined on the set A is equal to 1, 2, 3, 4. So now we are going to draw the Hasse diagram for it. So what is the Hasse diagram for it? We have to draw the Hasse diagram for it by using the three conventions. Convention number 1, every vertex will be represented with dot. Convention number 1 is, if the convention number 1 says that if there is a loop, here 1, 1 is there, right? You need not to exhibit these loops. Just represent them with dot. Just represent them with dot. So here dot 1 is nothing but 1, 1. Dot 1 is nothing but 1, 1. Says 1, 1 is there. Next 1, 2 is there. When there is a edge from 1 to 2, 1 must be downwards and 2 must be upwards. Look at this. I am drawing 1 downwards and 2 upwards. So there is a edge from 1 to 2. Dot 2 means 2, 2. Dot 2 means 2, 2. So 1, 2 is also over. Next, there is a edge from 1 to 3. 1 must be downwards and 3 must be upwards. 1 must be downwards and 3 must be upwards. So 1, 3 is over and 3, 3 is also over. 3, 3 is also over. Next one is 2, 4. 2, 4. So 2, 4 means 2 is downwards and 4 is upwards. So 2, 4 is over. 4, 4 is also over. Next 3, 4. 3, 4 means 3 must be downwards and 4 must be upwards. 3 must be downwards and 4 must be upwards. This is 3, 4. Now 1, 1 is over. I am representing that with dot. 2, 2 representing with dot. Next 3, 3 representing with dot 3. 4, 4 representing with dot 4. Next 1, 2. This is 1, 2. This is 1, 3. Next this is 2, 4. This is 3, 4. Now what happens? 1, 4. Now look at here. Look at the convention number 2. Convention number 2 says that if there is an edge from 1 to 2, 2 to 4, then definitely there will be the edge from 1 to 4. You need not to exhibit that edge separately. You need not to exhibit that edge separately. Therefore, this is the graph which is drawn by using the three conventions. Therefore, this is called the Hasse diagram of the given partial ordering relation. Now, I will see one more example. So, here I am taking some set. The set A is equal to 1, 2, 3, 4, 6, 8, 12. The partial ordering relation R on A is defined by A or B if and only if A divides B. If and only if A divides B. Then draw the Hasse diagram for R. So that is the relation. So what is the relation they have given? Divisibility relation. Divisibility relation on set of R, on the set 1, 2, 3, 4, 6, 8, 12. That is the set. Now this is the divisibility relation. So based on this divisibility relation, we will take the ordered pairs in that partial ordering relation. So the ordered pairs are like this. So 1 divides 1, 1 is dividing 1, 1 divides 2. So if you take number 1, 1 divides 1, 1 divides 2, 1 divides 3, 1 divides 4, 1 divides 5, 1 divides 8, sorry 1 divides 6, 1 divides 8 and 1 divides 12. So 1, 1 is there, 1, 3, 2 is there, 1, 3, 1, 4, 1, 6, 1, 8, 1, 12. Now take the second number. 2 will not divide 1. 2 will not divide, 2 divides 2. 2 will not divide 3. 2 divides 4. 2 divides 6, 2 divides 8, 2 divides 12. So 2 divides 2, 2 divides 4, 2 divides 6, 2 divides 8, 2 divides 12. Next third element, 3. 3 will not divide 1, 3 will not divide 2, but 3 divides 3, 3 divides 6, 3 divides 12. 3 divides 3, 3 divides 6, 3 divides 12. Next element is 4. 4 divides 4, 4 divides 4, 4 divides 8, 4 divides 12. Next element is 6. 6 divides 6, 6 divides 12. If you take the element 8, 8 will divide only 8. 8 will never divide any other elements. And if you take 12, 12 divides 12 only. 12 divides 12 only. So, if you take these elements and the relation between them is divisibility. The relation between them is divisibility. So, if A divides B is the divisibility relation, then that relation will be having all these ordered pairs. Now, for all these ordered pairs, we have to draw the assay diagram. Now, I am going to draw the assay diagram for this ordered pairs. Now, the first one is, yes. So, there is 1 comma 1. So, I am going to represent that with dot. Dot 1 means 1 comma 1. Next one is 1 comma 2. This is 1 comma 2. This is 1 comma 2. So 1 comma 2 is over and 2 comma 2 is also over. 2 comma 2 is also over. Next one is 2 comma 4. This is 4. So 2 comma 4 is over. 4 comma 4 is also over. From the transitive property, if there is a relation from 1 to 2, 2 to 4, then there must be 1 comma 4 also. 1 comma 4 is also over. Next, 1 comma 3. So 1 comma 3 is over. 1 comma 3 is over. 3 comma 3 is also represented. Next one is 3 comma 6. This is 6. So 3 comma 6 is over. Next 6 comma 6 is also over. Next, from the transitive property, if there is a relation from 1 to 3, 3 to 6, then there must be the relation from 1 to 6. 1 to 6 is also over. Next, 4 comma 8. This is 8. 4 comma 8. 4 comma 8 is over. Next, 8 comma 8 is also over. From the transitive property, if there is a relation from 1 to 4 and 4 to 8, then there must be the relation from 1 to 8. 1 to 8 is also over. Next, 6 comma 12. This is 12. 6 comma 12. Yes, 6 comma 12 is over. 12 comma 12 is over. From the transitive property, if there is a relation from 1 to 6 and 6 to 12, then there must be the relation from 1 to 12. 1 to 12 is also over. So now what are the remaining ordered pairs? 2 comma 6. So 2 comma 6. Now look at 2 is downwards and 6 is upwards. That is over. Next ordered pair is 3 comma 12. There is a relation from 3 to 6 and 6 to 12. There must be the relation from 3 to 12. Next ordered pair 2 to 8. If you look at 2 to 8, there is a relation from 2 to 4 and 4 to 8, then there will be the relation from 2 to 8. 2 to 8 is also over. Now 2 comma 12. 2 comma 12. So now look at this. There is a relation from 2 to 6 and 6 to 12. Therefore, there must be the relation from 2 to 12. Next 4 comma 12. So this is 4 comma 12. That is 4 comma 12. Next 6 comma 12. Now look at this. This assay diagram is going to represent all the ordered pairs which are there in this partial relation. 1, 1, 2, 2, 3, 3, 4, 4, 6, 6, 8, 8, 12, 12. Next 1, 2, 1, 4, 1, 8, 1, 3, 1, 6, 1, 12. Next 2, 4, 2, 2, 2, 4, 2, 6, 2, 12, 2, 8. Next if we take 3, 3, 3, 3, 6, 3, 12, over. Next the element 4, 4, 4, 4, 8, 4, 12. Next the element is 6, 6, 6, 6, 12. Next element is 8, 8, 8. Next element is 12, 12, 12. So this is the pictorial representation of the given partial ordering relation, which is drawn by using the three conventions. Therefore, this is the assay diagram for the example 2. This is how we are going to draw the assay diagram for the given partial ordering relation. Now, we will discuss one more important problem. This is very important problem. Yes. Draw the assay diagram for the positive divisors of 36. Here they have given the positive divisors of 36. So which is denoted as D36. The positive divisors of 36 are 1 divides 36. That is one positive divisor. 2 divides 36. 3 divides 36. Next 4 divides 36. 4 divides 36. Next 6 divides 36. 6 divides 36. 7 will not divide 36. 8 will not divide 36. Next 9. 9 divides 36. 10 will not divide 36. 11 will not divide 36. 12 divides 36. 13 will not divide 36. 14 will not divide. 15 will not divide. 16 no. 17 no. 18 divides 36. 18 divides 36. Next 19, 20 no. 21, 22, 23. And the next number which is going to divide 36 is 36 only. These are all the positive divisors of 36. 1 divides 36, 2 divides 36, 3 divides 36, 4 divides 36, 6 divides 36, 9 divides 36, 12 divides 36, 18 divides 36, and 36 divides 36. These are all the positive divisors. This is the given set A. This is the given set A. Now you need to find out the ordered pairs in the partial ordering relation R. So you need to find out the ordered pairs in the relation R. So what are the ordered pairs in the relation R? The ordered pairs in the relation R must and should satisfy divisibility property. Divisibility property means if you take two numbers, one number must and should divide and the number. So now here I am taking 1. 1 divides 1. 1 divides 2. That is 1 is dividing all other numbers. 1 divides 3. 1 divides 4. Next 1 divides 6. 1 divides 9. 1 divides 12. 1 divides 18. Next 1 divides 36. Comma. Next I am taking the second element 2. 2 divides 2. 2 divides 4. 2 divides 6. Next 2 divides 12. Next 2 divides 18. Next 2 divides 36. Next element 3. 3 divides 3. 3 divides 6. 3 divides 9. 3 divides 12. Next 3 divides 18. 3 divides 36. Next I am taking the element 4. 4 divides 4. 4 divides 8. 4 divides 8. 8 is not there. 4 divides 4. Next, 4 divides 12. Next, 4 divides 36. 4 divides 36. Next element is 6. 6 divides 6. 6 divides 6. 6 divides 12. 6 divides 18. And 6 divides 36. 6 divides 36. Next I am taking the element number 9. 9 divides 9. 9 divides 9. 9 divides 18. Next 9 divides 36. Next the element 12. 12 divides 12. 12 divides 36. Next the element 18. 18 divides 18. Next 18 divides 36. The next element is 36. 36 divides 36. These are all the ordered pairs in the relation R. So here if you take the elements, 1 is dividing all other elements. 2 is dividing 4, 6, 12, 18, 36. 3 is dividing 6, 9, 12, 18, 36. 4 dividing 4, 12, 36. 6 divides 6, 12, 18, 36. 9 divides 9, 18, 36. Next 12 divides 12, 36. 18 divides 18, 36. 36 divides 36. These are all the ordered pairs which are there in the given relation R, and this relation satisfies reflexive property, antisymmetric property and transitive property. Therefore, this is a partial ordering relation. Now I am going to draw the assay diagram for it. First, this is the element 1. This is the element 1. 1 is nothing but 1 comma 1 is over. I am representing 1 comma 1 with 1. Next 1 comma 2. Next one is 1 comma 2. 1 comma 2. So 1 comma 2 is over. 2 comma 2 is also over. Next 2 comma 4. This is 2. This is 4. 2 comma 4. So 2 comma 4. 2 comma 4 is over. 4 comma 4 is also drawn. Next, from the transitive property, if there is a relation from 1 to 2, 2 to 4, there must be the relation from 1 to 2, 1 to 4. 1 to 4 is also drawn. Next, 1 comma 3. 1 comma 3. So 1 comma 3. This is 1 comma 3. 3 comma 3. Next, 3 comma 9. 3 comma 9. 3 comma 9. So 3 comma 9. So 3 comma 9 is this one. 3 comma, this is the 3 comma 9. So 3 comma 9 is over. 3 comma 9 is over. From transitive property, if there is a relation from 1 to 2, 3 and 3 to 9, then there must be the relation from 1 to 9. 1 to 9 is also over. Next, 4 comma 12. Look at this. This is 12. 4 comma 12. So 4 comma 12 is over. 12 comma 12 is over. 12 comma 12 is over. Now, from transitive property, if there is a relation from 1 to 4 and 4 to 12, then there must be the relation from 2 to 12. 1 to 12. So 1 to 12 is also over. Next, again from the transitive property, if there is a relation from 2 to 4 and 4 to 12, then there must be the relation from 2 to 12. 2 to 12 is also over. 2 to 12 is also over. Next, 9 to 18. 9 to 18. So 9 comma 18 is over. This is 9 comma 18. 9 comma 9 is also over. 18 comma 18 is also over. So from the transitive property, if there is a relation from 1 to 9 and 9 to 18, then there must be the relation from 1 to 18. Similarly, there is a relation from 3 to 9, 9 to 18, there must be the relation from 3 to 18. Over. 3 to 18 is also over. Next, 36. I am taking 36 here. So this is 3 comma 36. That is 8 comma 36. 18 comma 36. 18 comma 36 is over. 36 comma 36 is over. Next, 12 comma 36. 12 comma 36 is over. Now, there is a relation from 4 to 12 and 12 to 36. Therefore, there will be the relation from 4 to 36. Over. Next, 6. Here I am taking 6 here. So, 2 to 6. 2 comma 2 is over. 6 comma 6 is over. Next, 2 comma 6 is over. Next, 3 to 6. 3 to 6. 3 to 6 is also over. 3 to 6. Next, 6 to 12. This is 6 to 12. 6 to 12 is also over. Next, 6 to 18. 6 to 18 is also over. Next, 6 to 36. Now look at, there is a relation from 6 to 18, 18 to 36. Therefore, there will be the relation from 6 to 36. Next, 9 to 36. There is a relation from 9 to 18, 18 to 36. Therefore, there will be the relation from 9 to 36. Next, 3 comma 12. There is a relation from 3 to 6 and 6 to 12. Therefore, there will be the relation from 3 to 12. Next, 3 comma 36. There is a relation from 3 to 18, 18 to 36. Therefore, there will be the relation from 3 to 36. 2 comma 36. There is a relation from 2 to 12 and 12 to 36. Therefore, there will be the relation from 2 to 36. Next, 1 comma 36. There is a relation from 1 to 12 and 12 to 36. Therefore, there will be the relation from 1 to 36. Next, 2 comma 18. There is a relation from 2 to 6 and 6 to 18. Therefore, there will be the relation from 2 to 18. 1 comma 6. There is a relation from 1 to 2, 2 to 6. Therefore, there will be the relation from 1 to 6. So now if you look at all the ordered pairs, all these ordered pairs are represented in this graph. All the ordered pairs are represented in this graph by using the three conventions. Therefore, this is the Hussey diagram for the positive divisors of 36. When you look at this, 1 comma 1, 1 comma 2, 1 comma 3, 1 comma 4, 1 comma 6, 1 comma 9, 1 comma 12, 1 comma 18, 1 comma 36. Next 2, 2 comma 4, 2 comma 6, 2 comma 12, 2 comma 18, 2 comma 36. 3, 3 comma 3, 3 comma 6, 3 comma 9, 3 comma 12, 3 comma 18, 3 comma 36. Next 4, 4 comma 4, 4 comma 12, 4 comma 36. Next 6, 6 comma 6, 6 comma 12, 6 comma 18, 6 comma 36. Next 9, 9 comma 9, 9 comma 18, 9 comma 36. 12 comma 12, 12 comma 36. 18 comma 18, 18 comma 36. And 36 comma 36. So whatever representation, whatever pictorial representation I have drawn by using three conventions, this will be the Hussey diagram for the positive divisors of 36. If you take 36, these are all the positive divisors. 1, 2, 3, 4, 6, 9, 12, 18 and 36. And the relation between them is the divisibility relation. And you will be having all these ordered pairs. If you represent all these ordered pair in this graph by using three conventions, then you will be getting the Hussey diagram. This is the required Hussey diagram for the given positive divisors of 36. So this is how we are going to draw the Hussey diagram for the given partial ordering relation. Remember, this Hussey diagram is drawn for only partial ordering relation. If the relation is not partial ordering relation, then there exists no Hussey diagram. The Hussey diagram will not be there for equivalence relation because it is not partial ordering relation. So this is about assay diagram. So now I'll see the next relation. Yes, next we see what is function. Next we discuss about functions. Yes, we discuss about the functions. Now I will give you the definition of function. Before I am going to explain about the function, let me explain about the total order. So I am going to explain about total order. Total order. Total order. So this total order is defined for the partial ordering relation. So whatever relation we are taking, it must be partial ordering relation. So if R is partial ordering relation, then we can define the total ordering relation for it. So in order to partial ordering relation means it must be reflexive. It must be reflexive. This is first property. Then it must be antisymmetric. It must be antisymmetric. And the third one is it must be transitive. It must be transitive. So if R satisfies these three properties, then it is called partial ordering relations. In addition to these three properties, if R satisfies one more property, then it is called partial ordering relation. What is that property? This is the fourth property. For any A comma B belongs to set A. If you take any two elements from the set A, there must be A or B or B or A. So in addition to reflexive relation, antisymmetric property and transitive property, if R satisfies this property, what is this property? If you take any two elements in set A, then there must be the relation from A to B or B to A. A or B means A may be related to B or B may be related to A. So for every two elements in the set, if one element is related to another element, so that one is element is related to another element means there may be relation from A to B or B to A. Any one of them must be there. Then it is called total ordering relation. Then it is called total ordering relation. This total ordering relation is for only partial ordering relation. Partial ordering relation means which is reflexive, antisymmetric and transitive. In addition to these three properties, if R satisfies what is that? This property, then R is the total ordering relation. So property number 4 says there must be the relation from A to B or B to A. There must be the relation from A to B or B to A. Now I will take one example. We already seen that the set of all real numbers, comma less than or equal to. This is a post set. We already in the beginning of this session, I explained that less than or equal to is a partial ordering relation or set of all real numbers. Now I am going to verify whether this less than or equal to is satisfying this property or not. Now take any two real numbers, 2 comma 3. Yes, 2 is less than or equal to 3. That means there is a relation from 2 to 3. Likewise, take any two real numbers, then one of the real numbers. If you take two real numbers A and B, obviously one real number will be lesser than the other real number, which is nothing but there will be the relation from one element to another element. Here less than or equal to is a total ordering relation. Similarly, this one, R comma greater than or equal to. R comma greater than. We already seen that R comma greater than or equal to is a post set. Here if you take two real number, then one real number must be greater than another real number. Not only 3 comma 2. Take any two real numbers on your choice. If you take minus 1 comma 0, obviously 0 is greater than or equal to minus 1. There is a relation from 0 to 1. Take 5 comma 10. If you take 5 comma 10, 10 is greater than or equal to 5. There is a relation from 10 to 5. Take 6 comma 5. 6 is greater than or equal to 5. There is a relation from 6 to 5. So likewise, if take any two real numbers, one will be obviously greater than or equal to another one. Therefore, the relation greater than or equal to and less than or equal to, both of them are total ordering relation. This is about the total ordering relation. So total ordering relation means the relation must and should satisfy reflexive property, antisymmetric property, transitive property. In addition to these three properties, this additional property must be satisfied. What is the additional property? If you take any two real numbers a and b, there must be relation from either a to b or b to a. Then we say that the given relation is total ordering relation. So this is all about the relations and their properties. Now we'll see what are the functions and what are the properties of those functions. Now function. So already we have seen that relation is a subset of Cartesian product. Then what is a function? Look at, a function is a relation. Function is a relation. Function is a relation from capital A to capital B such that for every element in BA, there must be a uniquely associated element in B. There must be a uniquely associated element in B. Then we say that that relation is function. So what is function? Function is a relation from set A to set B such that for every element in set A, there must be a uniquely associated element in set B. Then that relation is called function. That is one definition. The other definition is, if I take two non-empty sets, A and B are two non-empty sets, then a relation, a function or mapping, the function is also called mapping. Function or mapping from A to B is a relation from A to B such that for every element in set A, there must be a uniquely associated in set B such that A comma B belongs to F. Such that A comma B belongs to F. Now we'll see what is the pictorial representation of this. So it is like this. So I am taking set A, this is set A, and this is set B. F is the mapping or function from A to B. F is the mapping or function from A to B. If you take any element in this set, then there must be the mapping in this. There must be the mapping in this. Then it is called function. So for every element in set A, there must be the uniquely associated element in set B, then it is a mapping. For example, if you take the element like this, 1, 2, 3, this is like A, B, C. If you take one more element 4, then this is not a function. So this mapping is not a function. The reason is that the element 4 is not having any uniquely associated element in B. With that reason, this is not a function. If you remove 4, then it becomes function. If you remove 4, then it becomes function. So function is nothing but take every element in A, there must be the uniquely associated element in set B, then it is called function. Now if you take like this, if you map like this, now also this is not a function. The reason is that the element 1 is having two elements in B. That means 1 is mapped to two different elements. 1 is mapped to two different elements. According to the definition of function, if for every element in A, there must be uniquely associated mapping. Uniquely associated mapping. But the element 1 is mapped to two different elements. Therefore, this is not a function. So, if for every element in A, if there is a uniquely associated element in B, then it is called function. Now, these are all some other points related to function. Here, I told you that there is a mapping like this. This is A and this is B. This is the mapping F from A to B. If you take A and this is the mapping for it. So, here B is called image. So, A is mapped to B, right? So what is the name of B for A? B is called the image of A. B is called the image of A. B is called the image of A. And conversely, A is the pre-image of B. A is called pre-image of B. So for this mapping, B is called image of A and A is called pre-image of B under the function f. And one more point, this one. Here A is also called argument. Here also A is also called argument for the function, and B is equal to f of A is called the value of the function under the value of the function for the argument A. So if you take some function f of x, if you take some function f of x, or if you take some function f of A, and this is the value of A, this is the f of A is the value for the argument A. That is the meaning of this one. A function from A to B is denoted like this. F maps A to B. It is read as F maps A to B. F maps A to B. The pictorial representation of a function A to B. This is the pictorial representation of the mapping. This is set A and this is set B, and this is the mapping F. This is A set and this is B set. Take some different elements and map it to different elements in B. You can map them in any way, but make sure that every element in set A is going to have only unique mapping. Every element of set A is having only unique mapping in set B. This is about the function. Now we'll see what is domain, codomain. Now, and one more thing. Let N be two finite sets with cardinality of A is equal to M and cardinality of B is equal to N. Then the number of functions from A to B. So this is some set A and this is from set B, and F is the mapping from set A to set B, and here set A is having M elements, A1, A2 and so on AM. Set B is having N elements, B1, B2 and so on Bn. So the cardinality of A is M, the cardinality of B is N. The cardinality of B is N. Then how many relations, how many functions are possible from A set A to B? So the number of relations from set A to B means, now here set A is having M elements, set B is having N element. Now take the first element A. A can be mapped with any one of the elements in B. A can be mapped with any one of the elements in B. That means to map this element we have N possibilities. To map A1 we have N possibilities. Similarly, to map A2 we have N possibilities, and so on. To map AM we have N possibilities. So the set A is having M elements, and for every element there are N possibilities, N into N up to M times, which is nothing but N power M. There will be N power M functions from set A to set B when set A is having M elements and set B is having N elements. Then we see what is the domain, codomain and range. So here let me explain this with simple example. So F is the mapping from A to B. I am taking some elements in set A, 1, 2, 3, 4, and some elements in set B, A, B, C. A, B, C. Now 1 is mapped to A, 3 is mapped to B, 2 is mapped to C, and 4 is mapped to C. 4 is mapped to C. So now here there is one more element D here. There is one more element D here. So here F is a function from A to B. F is a function from A to B. The set of all elements in set A is called domain. Domain is set of all elements. Domain is equal to the set of all elements in set A, 1, 2, 3, 4. This is called domain. Next, codomain. Codomain. Next, range. Range. So range is nothing but the set of all images of capital E. The set of all images of the elements in capital A is called image. So for 1, A is one image. Next, for 2, C is one image. For 3, B is the image. For D, C is the image. That means the range set will be having A, comma, B, comma, C. That means these 3 are the images for these elements. These 3 are the images for these elements. So range is nothing but the set of all images of capital A. Codomain is nothing but the set of all elements in B, that is A, comma, B, comma, C, comma, D. So the set of all elements in A is the domain. The set of all elements in the B is the codomain. The set of all images in B is called range. This is about domain, codomain, and range. So these are the definitions. With this simple example, you can understand that the set of all elements in A is called domain. The set of all elements in B is called codomain. And the set of all images, is called range. Here you must understand that range is a subset of codomain. Range is a subset of codomain. Range is a subset of codomain. So this is all about domain, codomain, and range. So these are all the different definitions for them. If you see the definitions, these are the definitions. The range of the function f maps A to B is denoted by f of A and is defined as set of all images of the elements of A. So this is the symbolic way of defining it. F of A is equal to f of x such that x belongs to A. Here what is f of x? For x, the image is f of x. For the element x, the image is f of x. So now note this point. For the mapping, A maps A to B, if B belongs to B and F inverse of B is defined as, F inverse of B is defined by like this. So here, this F inverse of B is called all pre-images. The F inverse of B is called the set of all pre-images. F of B is the image and F inverse of B is the set of all pre-images. Yes, so F of B is having the set of all pre-images. So for any mapping, for any function f maps A to B, F inverse of B is called the set of all pre-images of capital B. The set of all pre-images of capital B. Now I'll see the different types of the functions, and these are some examples based on the functions. Here I have taken some example. This is set A, this is set B, and R be the relation from set A to set B defined by like this. Now is R is function. Now they have given this problem. We have to verify whether this is function or not. It's the better way to understand this problem is draw the Venn diagram or pictorial representation of it. The Venn diagram for this one is, this is F, this is set A, and this is B. This is R. They have given R. R is the relation from A to B. A is having 3 elements, 1, 2, 3. B is having 2 elements, minus 1, comma 0. Minus 1 is mapped to minus 1. Next 1 is mapped to 0. Next 2 is mapped to 1. 2 is mapped to minus 1. Next 3 is mapped to 0. 3 is mapped to 0. Now is it function? No, this is not the function. Why it is not function? The element 1 is having 2 images. That means the element 1 is mapped to 2 elements in set B. The image 1 is mapped to 2 elements in set B. That means the element 1 is having 2 different elements in set B. That means 2 different images. According to the definition of function, if every element of A is uniquely mapped with the elements of B, then it is called function. So function is nothing but for every element in set A, there must be only unique mapping. If there is more than one mapping, then it is not a function. So whatever example they have given, that is not a function. The reason is that the element 1 is mapped to 2 elements. That is, the element 1 is having 2 images, minus 1 and 0. With that reason, this is not a function. Now I'll see some other examples. So here they have given set A and set R. F is the mapping from A to R. R is set of all real numbers and f of x is this. And find the range of f. You need to find out the range of f for these elements. First we will find out the range of 0. First we find range of 0. So range of 0 is nothing but f of 0. So they have given f of x. So x square minus x plus 1. Put x equal to 0. 0 square minus 0 plus 1, which is nothing but 1. Next, the range of the element 1 is nothing but f of 1. This is equal to 1 square 1, 1 plus 1, which is nothing but 1. Next, range of the element minus 1. The range of element minus 1 is f of minus 1, which is equal to minus 1 whole square minus of minus 1 plus 1, which is equal to 1 plus 1 plus 1, which is 3. Next, the range of the element 2, which is nothing but f of 2. F of 2 is equal to 2 square minus 2 plus 1. That is 4 minus 2 plus 1, which is nothing but 3. Next, the range of the element minus 2 is f of minus 2. This is equal to minus 2 whole square minus of minus 2 plus 1, which is nothing but 4 plus 2 plus 1, that is 7. That is 7. So now what is the range of f? Range of f is equal to the set of all images. So what are the images? 1, 1, 3, 3, 7. This is the range of the given, that is the range of f of x. This is about this problem. Now next one. Now we'll see the types of the functions. There are different types of functions. Now we are going to discuss all these functions with examples. The first one is identity function, and the second one is constant function, and then we have onto function, and then we have one-to-one function, then we have one-to-one correspondence. So identity function, constant function, onto function, one-to-one function, one-to-one correspondence. Now I'll see one by one with definitions and examples. So now this is the definition of one-to-one function. So this is the definition of identity function. Now look at what is the identity function if f of a is equal to a. If f of a is equal to a. So if you take element a, the image of a is f of a. The image of a is f of a. So a is some element and f of a is the image of a. If both of them are equal, then we say that mapping is identity mapping. That means if every element is mapped to itself, then it is called identity function. For example, this is set A and this is also set A. This is the mapping from A to A. That is the mapping from A to A. 1, 2, 3. 1, 2, 3. So 1 is mapped to 1, 2 is mapped to 2, 3 is mapped to 3. That means the image of every element is itself. Such type of functions are called identity functions. If a function is an identity function, then the mapping image of every element is itself. Now look at this is one definition and this is the another definition. If you take the identity function, then f of a is equal to a. This is the very important bit. F of a is equal to a is nothing but the range of a is f of a. If range and domain are same, then it is called identity function. The identity function is denoted by IA or 1A. This is about the identity function. Next, this is the Venn diagram for it. This is the Venn diagram for identity function. This is f a to a. If you take the element a, and there will be the image a only. A is mapped to a itself. These are the examples. If you look at this one, 1 is mapped to 1 itself, 2 is mapped to 2 itself, 3 is mapped to 3 itself. That means whatever function they have given, that is the identity function. The reason is that the image of 1 is 1 itself, the image of 2 is 2 itself, the image of 3 is 3 itself. So this is about identity function. Next, this is the another example for the identity function. The next one is constant function. So constant function means for every element in set A, there is only one image. For every element in set A, there is only one image, then it is called constant function. So this is F, this is set A, and this is set B, 1, 2, 3. Okay. For A1, the image is K, for 2, the image is K, for 3 also the image is K. So that is, for every element in set A, if there is only unique image, for every element in set A, if there is unique image, then it is called constant function. So if any function is constant function, then the image will be having only one element. The range f of A is the range of A, right? So the range set will be consisting of only one element. So if a function is constant function, then the range set will be consisting of only one element, because every element in set A will be mapping with that element only. This is about the constant function. Then these are the examples. If you look at this example, 1 is mapped to A, 2 is mapped to A, 3 is also mapped to A. That means for every element in set A, there is only one image, that is A. The next one is onto function. Now look at this onto function. A function f maps A to B is said to be onto function if every element of B has a pre-image. If every element of the domain is having the pre-image, then it is called onto function. And this is the other definition. Look at, if any function is onto, then this condition is satisfied. So if the range and codomain are same, then that function is called onto function. When the range and codomain are same, if every element in codomain is having the image in pre-image in set A, then f of A is equal to B. This onto function is also called surjective function. The onto function is also called surjective function. If a function is onto function, then onto function is also called surjective function. And this is the Venn diagram for the onto function. This is F, this is set A, and this is set B, some element A, B, C. Then 1, 2, 3. So A is mapped to 2, B is mapped to 1, C is mapped to 3. Now look at this. For every element in set B, there is a pre-image. For every element in set B, there is a pre-image. So what is the range of this function? 1, 2, 3. What is codomain? 1, 2, 3. Range and codomain are same for the onto function. This is about the onto function. And this is the example. If you look at this example, look at, there are 3 elements in set B. For these 3 elements, there must be the pre-image. So for A, 1 is the pre-image. For C, 2 is the pre-image. For B, 3 is the pre-image. That means every element in set B is having the pre-image. Therefore, this function is onto function. The next one is one-to-one function. There are different definitions for one-to-one function. The simple definition is, if you take 2 different elements in set A, there must be 2 different images in set B. For every 2 different elements in set A, there must be 2 different images in set B. Then we say that that function is one-to-one function. So these are 2 different definitions. A1 is not equal to A2 is nothing but different element. If A1 and A2 are different, then their images are also different. If A1 and A2 are equal, then their images must be equal. So this is one definition. These 2 are the 2 different definitions. If you take different elements in set A, there must be different images. If you take equal elements, there must be equal elements. This is about one-to-one function. The one-to-one function, look at, if f maps A to B is a one-to-one function, then every element of A has a unique image in B. if you take one-to-one function, for every element in set A, there must be unique image in set B, and for every element in set B, for every element in f of A, there will be unique pre-image in set A. So, if any function function is one-to-one, then for every element in set A, there will be unique image in set B, and for every element in f of A, there must be unique pre-image in A. Then it is called one-to-one function. So the one-to-one function is also called injective function. The one-to-one function is also called injective function. If we take the Venn diagram for it, this is mapping from A to B, this is A, this is B. 1, 2, 3, A, B, C. 1 is mapped to B, 2 is mapped to C, 3 is mapped to A. Now look at different elements are having different images. So for every element in set A, there is unique image. For every element in f of A, there is unique pre-image. Therefore, this is called one-to-one function. Now this is the example. 1 to 1. So 1 and 2 are two different elements, their images are also different. 2 and 3 are two different elements, their images are also different. That means different elements in set A are having different images, therefore it is one-to-one function. Now I'll see what is one-to-one correspondence. So one-to-one correspondence means which is both 1, 1 and onto. Any function, if it is both 1 to 1 and onto, then it is called one-to-one correspondence. And the another definition for this is, for every element in set A, there is unique image in set B, and for every element in set B, if there is a unique image in set A, then that is called one-to-one correspondence. The one-to-one correspondence is also called bijective function. So onto function means surjective function. One-to-one function means injective function. One-to-one correspondence means bijective function. By 1, 1 and onto. This is about the bijective function. So the Venn diagram for the bijective function means same. This is the Venn diagram for bijective function. This is F, this is A, this is B, A, B, C, 1, 2, 3. 1 is mapped to 3, B is mapped to 3, 1, and C is mapped to 2. Now look at different elements are having different images. Therefore, this is one-to-one function. For every element in set B, there is a unique image onto. That is both 1, 1 and onto. Therefore, that is one-to-one correspondence function. These are all the different functions. These are all the different types of functions. Now look at this example. This is 1, 1. Different elements. If you take the pictorial representation of this, it is looks like this. This is F, set A, set B. The elements set A are 1, 2, 3. The elements in set B are A, B, C. Next, 1 is mapped to A, 2 is mapped to C, 3 is mapped to B. So this is 1, 1 because different elements are having different images. Next, second one, for every element in B, there is a pre-image in set A. That is 1, 1 and both 1, 1 and onto. Therefore, that is one-to-one correspondence function. Now look at, I am taking some mappings, we'll see what are the types of these functions. The first one, so what type of function it is? The image of every element is itself. The image of every element is itself. 1 is mapped to 1 itself, 2 is mapped to 2 itself, 3 is mapped to 3 itself. Therefore, this is identity function. This is identity function. Next, now look at this. 1 is mapped to 2, 2 is mapped to 1, 3 is mapped to 1, 2. If you take the pictorial representation of this, so this is mapping from A to B. A is having 3 elements and this is the mapping from A to A itself. 1, 2, 3, 1, 2, 3, next 1, 2, 3. So here 1 is mapped to 2. Next 2 is mapped to 1 and 3 is mapped to 2. 3 is mapped to 1, 2. So what is this one? That is function. Is it one-to-one function? No. 1 and 3 are two different elements, but they are having same image. So that is not a one-to-one function. Is it onto? No. Is it onto? One-to-one means different elements should have different images. Is it onto function? Yes. So for every element in set A, that is for every element in f of A, f of A is nothing but 1, 2. For these two elements, there is a image. There is a image, pre-image. Therefore, this function is 1, 1, but not onto, because the element 3 is not having any pre-image. The element 3 is not having any 3 image. Therefore, this is only just function. It is not 1, 1, and this is not 1, 2. And look at this one. If you look at this, 1 is mapped to 2, 2 is mapped to 2, 3 is mapped to 1. So 1, 2, 3, 1, 2, 3, 1, 2, 3. This is the mapping F from A to A itself. 1 is mapped to 2, 2 is mapped to 2, and 3 is mapped to 1. 3 is mapped to 1. Same, that is only function, but it's not one-to-one and onto. Now what about this? This one is 1, 2, 3, 1, 2, 3. 1 is mapped to 2, next 2 is mapped to 3, and 3 is mapped to 1. This is the function. That is 1, 1 function, that is onto function, and this is one-to-one correspondence also. So these are the different problems based on types of the functions. Now look at this. They have given some function. They have given some function. For all A belongs to Z, find whether F is 1, 1 or not. F is 1, 1 or not. So take two different elements. A1 and A2 are two different elements. A1 is not equal to A2. Now what you have to prove? You have to prove that F of A1 is not equal to F of A2. What is F of A1? The image of A1. F of A2 is image of A2. If you take two different elements, then their images must be different. So how to prove it? So they have given F of A. So A1 is not equal to A2. Add 1 on both the sides. A1 plus 1 is not equal to A2 plus 1. So A1 plus 1 is F of A1. This is F of A2. So if you take two different elements, then their images are also different. Therefore, F is one-to-one function. F is one-to-one function. Now what about onto function? This is our onto function. So B belongs to Z. For every element in B set, there is an image. What is that image? B minus 1 is the image, such that F of A is equal to B. Such that F of A is equal to B. That is, for every element in the codomain, there is a pre-image in set A. Therefore, the function is onto. So 1, 1 and onto. Therefore, whatever function they have given, that is one-to-one correspondence function. This is some other example, very simple one. You can go through it. You can easily understand this. Next, composition of function. So the composition of function, here I am taking three sets, A, B, C, and two functions. F is a function from A to B, and G is a function from B to C. Then the composition of F and G. This is A, this is B, and this is C. So F is a function from A to B. G is a function from B to C. And this is G circle G, G circle F. G circle F is a function from A to C. G circle F is a function from A to C. If you take element A, the image of A is F of A. The image of F of A is G of F of A. G of F of A. So, image of A is F of A under function F. The image of F of A under G is G of F of A. So, this is our composition of F. So, F is a function from A to B and G is a function from B to C. Then G circle F is a function from A to C. G circle F is a function from A to C with G of F of G circle F of A is equal to G of F of A. G circle F of A is equal to G of F of A for every element A belongs to A. Then this is the composition of G and F. So here, and one more thing, look at this. For any function f maps A to B, G's f circle f is called f square. F circle f is called f square, and f circle f square is nothing but f cube. The composition of f and f is f square. The composition of f and f square is f cube. This is about the composition of function. And these are the examples. This is the example. They have given some function f. So this is the function f. So this is the function f. And this is the function z. F function, g function. Find g circle f. So what is g circle f? G circle f of 1. What is the g circle f of 1? You are asked to find out g circle f. G circle f of 1. G circle f of 1 is equal to g of f of 1. So this is equal to g of f of 1. What is f of 1? This is the f function, right? 1 is mapped to a, g of a. So what is g of a? This is the g function. A is mapped to x. That is the x. G circle f of 1 is equal to x. G circle f of 2 is equal to g of f of 2, which is nothing but g of f of 2. F of 2 means 2 is mapped to a. G of 2, again this is equal to x. Next, g circle f of 3 is equal to g of f of 3. So f of 3 is equal to, f of 3 is b, g of b. G of b is equal to, what is that? Y. Next, g circle f of 4. G circle f of 4 is equal to g of f of 4, which is equal to g of f of 4. F of 4 is nothing but c. G of c, which is nothing but z. So this is g circle f of 1, g circle f of 2, and g circle f of 3. Now we'll see what is the invertible function. So what is the invertible function means? Now f is the function from a to b. The function f maps a to b is said to be invertible function if there exists a function g maps b to a such that g circle f is equal to ia and f circle g is equal to ib, where ia is the identity function on a and ib is the identity function on b. Then we say that f and g are inverses to each other. F and g are inverses to each other. So when we say that this function is invertible function, if there is a function g maps b to a such that g circle f is equal to ia and g circle b is equal to ib, then we say that the function f is invertible and the inverse of f is g. Similarly, the inverse of g is f. This is about the invertible functions. So here g is called the inverse of f and is denoted like this. G is equal to f inverse. Now this is the example. This is the example. So they have given some function f and they have given some function g. They are asking us to verify whether they are inverses to each other or not. So here I am finding g circle f of 1, which is nothing but 1, identity function, identity element. G circle f of 2, which is 2. G circle f of 3, 3. G circle f of 4, 4. That is g circle f of a is equal to ia. Similarly, f circle g. F circle g of 1 is this, 1. F circle g of 2 is 2. F circle g of 3 is 3. F circle g of 4 is 4. Therefore, for all x belongs to a, g circle f of x is equal to ia of x and f circle g of x is equal to ia of x. That means g circle f of x and f circle g of x are identity functions. Therefore, f and g are inverses to each other. Both of them are inverses to each other. That means F is the inverse of G and G is the inverse of F. So this is some other example. You can easily go through this one. This is a very simple one. You can go through it. Then these are some other problems. Now we'll see the pigeonhole principle. This is very important one. Pigeonhole principle. Why it is important means there is a subject called theory of competition, that is formal languages and automata theory. In formal languages and automata theory, there is a lemma called pumping lemma. There is a lemma called pumping lemma. To prove the pumping lemma, this pigeonhole principle is used. That means the pumping lemma is based on the pigeonhole principle. So what is pumping lemma? That pumping lemma is used to prove that the given sets are not regular. To prove that, we are going to use the principle of pigeonhole principle. Now I'll see what is the pigeonhole principle. This is the statement for pigeonhole principle. There are m pigeons and there are n pigeonholes. If m is greater than n, then two or more pigeons occupy the same pigeonhole. That means, let me explain this with simple example. There are two benches, which each is 3-seater. There are two benches and there are 7 students. How to arrange these 7 students in 2 benches? So 3-seaters, the first bench 3 students can sit, the second bench 3 students can sit, 3 plus 3, 6. One student is extra is there, right? That students can be arranged in either bench 1 or bench 2. That means if the number of students are more than number of benches, then obviously the benches are going to have more than 3 students. So here, if m is the pigeons and n is the pigeonholes, if the number of pigeons are more than pigeonholes, then at least one pigeonhole must and should have more than 2 pigeons. That is the pigeonhole principle. And this is the understatement for it. And this is the generalized pigeonhole principle. The generalized pigeonhole principle says that if m is the pigeons, if m pigeons occupy n pigeonholes and m is greater than n, then at least one pigeonhole must contains p plus 1 or more pigeons. Here p plus 1 is equal to m minus 1 divided by n. M minus 1 divided by n. Simply we can say that if the pigeonholes are less than number of pigeons, obviously any one of the pigeonhole will be having more than 1 pigeons. This is the pigeonhole principle. This principle will be used in pumping lemma, which is there in the formal languages and automata theory. So, and these are the examples. So, if you look at this example, there is a bag contains 12 pairs of socks, each pair in different colors. If a person draws the socks one by one at random, determine at most how many draws are required to get at least one pair of matched colors. So here there is a box which is having 12 different colors of different pairs of socks. There is a box which is consisting of 12 different pairs of socks. So if we are drawing socks one by one, then how many number of attempts we have to attempt to have the matched pairs? We have the matched color socks. The reason is very simple. If you draw the socks 12 times, there are chances to get 12 different colors. If you draw the 13th one, the 13th one will be matching with any one of the 12 colors. So the maximum number of attempts you need to attempt is 13. Maximum number of colors you need to select is 13. This is the answer for this one. And this is some other answer, some other problem. Here they have proved that if 30 dictionaries in a library contains a total of 61,327 pages, then at least one of the dictionaries must have at least 2045 pages. So m value is 61,327, n value is this, then one dictionary must and should contain p plus 1 or more pages. Here p is equal to this minus 1 divided by 30 plus 1, and this is the answer for this. So this is a simple problem. Now we'll see some of the previous gate questions. So before we are going to end the session, let me quickly explain what I have explained in this session. I explained about the partial ordering relations. Partial ordering relation means which is reflexive, antisymmetric and transitive. Then I explained the total ordering relation. Then I explained the assay diagram. Then we have discussed about the functions, the types of the functions, composition of functions and invertible functions. Now we'll see some of the previous gate questions which are there in the previous question papers. So this is the question which is given in gate 2 1995. This is the question which is there in the gate 1995. So the question is, the number of elements in the power set P of S of the set A is equal to this. Is dash. So that is the answer. So when in one of the previous sessions I explained about the power set of a set. Power set of a set. So if you take any set A, then the power set of A is denoted with P of A. When I was explaining about the power set of A, I have explained very important formula. If the cardinality of A is equal to n, then the cardinality of P of A is 2 power n. That means if the set A contains n elements, then the power set of A contains 2 power n elements. So now what they are giving, they are asking, they have given set A and they are asking the number of elements in P of S. So in set A, how many elements we have? This is 1, this is 2 and this is 3. There are 3 elements in set A, therefore there will be 2 power 3 elements in P of S. There will be 2 power 3 elements in P of S. That is the answer. 2 power 3 is nothing but 8. There will be 8 elements in the P of S. That's the answer. So the correct answer is 8. The correct answer is 8 because the set A is having 3 elements, then the power set of S will be having 2 power 3 elements, that is 8. Now we'll see the next problem. This is given in gate 2015. So the question is, for a set A, the power set of A is denoted by 2 power A. The power set of A is denoted by 2 power A. So if A is equal to this, then which of the following are true? Which of the following are true? So these are the options. Now look at, they have given set A. Now what is power set of A? The power set of A will be having these elements. The power set of A will be having these elements. So empty set is a subset of every set. Empty set is a subset of every set. And there will be 5, there will be 5 comma 6 and like this. These are all the elements in power set of A. These are all the elements in power set of A. Here, if you look at this, this is a subset. This is subset. This is also subset. Now look at this. Is pi belongs to 2 power A? 2 power A is nothing but P of A. So empty set is a subset of power set. Therefore, this is correct answer. And this 5 element will be there in power set. And 5 comma 6, this element is also there in the power set. When you look at this, these elements will not be there in the power set. The power set will not be having the elements 5 comma the set 6. Therefore, the correct answer is 1, 3 and 5. This 1, 3 and 5 are correct. So empty set is a subset of power set and empty set will be there in the power set and this set is also there in the power set. But when it comes to this one will not be a subset of 2 power S, 2 power A. Now the next one is, I am taking this problem. It is given in gate 1996. A and B are 2 sets and A dash and B dash denotes the complements of A and B respectively. Now the set A minus B union, B minus A union, A intersection B is dash. These are all the options. Now we will find, first we will draw what is A minus B. So this is A minus B. If you draw A minus B, this is A, this is B. So A minus B means the exclusive region of A. This is A minus B. Next, B minus A. This is B minus A. This is B minus A. This is set A, set B. B minus A is nothing but the exclusive region of B. Next, A intersection B. This is A intersection B. This is A intersection B. This is A, this is B. Now what I am doing, I am going to union them. I am going to union the shaded region which is there in these three pictorial representations. This is A, this is B. So I am combining this shaded region, then you will be getting this. So A minus B means this region. This is A minus B. Next, B minus A means this region. I am combining this region also. Next, A intersection B means this region. So now if you look at this total region, this is A union B. That is A union B. So the correct answer is A union B. The correct answer is A union. So that means the set A minus B union, B minus A union, A intersection B is equal to A union B. If you combine these three regions, then you will be getting the region which is there in the A union B. These are some of the previous questions which I have found in the previous question paper. This is all about the today's session. Thanks for watching.